Okay, so it's my great pleasure to introduce today's CAIS seminar speaker, Professor Ajitesh Srivastava. He's a research assistant professor at ECE here at Viterbi School of Engineering at USC, and also our very own associate co-director for the Center for AI in Society. And so today we're going to get a chance to hear about Ajitesh's work, which was recently recognized by Triple AI Best Paper Honorable Mention Award at the Special Track for AI for Social Good. Ajitesh overall works on research in social networks, parallel computing, and machine learning for social good, crime, and computer architecture.
I don't work on crime, but just to clarify. Crime is not. I'm just saying I don't do crime.
You don't do crime. Yes.
So you would say.
So without further ado, thank you, Ajitesh, for agreeing to give a talk.
All right.
Welcome.
Thank you. Thank you. I'll quickly share my screen and start. Okay, as Bisra mentioned, this is a paper that appeared at Triple AI. This is called Nowcasting Temporal Trends Using Indirect Surveys. This is done in collaboration with IMDA Networks Institute in Spain. So we have a bunch of colleagues here listed. Before I start into this topic, I want to give you just a little bit of flavor of what I've been doing since not since my birth, it is minus infinity, but in research in general, just before PhD and during my PhD. And this can be broadly categorized as, in the entire spectrum of going from abstract, experimental, and real world. So abstract, where you have some mathematical formulation, and you come up with provably correct results. So I did some work there. And then there's the experimental work where you have some benchmarks, some data sets, and you come up with new methods, and you demonstrate success there. And then there is the type of work that we do a lot in CAIS as well, where there's a real world, data comes from the real world, and we come up with a solution that is deployed in the real world. So I've done work in this entire spectrum, but in general, you could say that it's really a combination of these three things: algorithms, network science, data mining, a term of the past decade. I guess now I should just say machine learning. More about my real work, real recent work. I've done some work in graph neural networks, where we're looking at subgraph-based methods for fast and accurate GNNs, also creating sparse GNNs so we can run these models fast, and also applying these GNNs in the real world applications. And over the last 3 years, I have done a lot of work in infectious diseases, where I work with the CDC and European CDC on problems related to COVID-19, influenza, and RSV. And this can be categorized as forecasting work and scenario modeling work, where the policymakers they tell us that this is the decision that we are wondering about. Should we do this versus should we do that? And then I, along with other colleagues, we try to work on this problem and come up with what would happen if you do this versus that. That is scenario model. But what we're presenting here has nothing to do with any of this, and it's something I might never do again because I feel like we've solved the problem. But I would like to introduce how this work came into play. So I would start with a warning: machine learning is infectious. So watch out. So our colleagues at IMDA Networks, they were looking at this sort of survey data. And this was data collected by the Delphi group at Carnegie Mellon. And this was collected over time, and this was collected through partnership with Facebook. So, randomly you will get these questions on Facebook and you would answer, and these survey results will be stored. And there were hundreds of questions over the period of 2.5 to 3 years. And the questions could be something like, in the past 24 hours, have you or anyone in your household experienced a fever along with cough, shortness of breath, or difficulty breathing? There were similar questions about mask use, like do you wear a mask when you go out? Vaccines, if a vaccine is available, would you take it? Have you taken the vaccine? So there were order of hundreds of questions of this type. And what they were trying to do, by they I mean the IMDA Networks group, they were using the response of these 50 to 100 questions and using them as features to sort of nowcast or detect or predict the number of COVID-19 cases. Okay, so you have these 50 to 100 questions, and those act as your input. Output is the prevalence of COVID-19. And they came to me as a machine learning expert, like, is this the right way to do it? What else can we try? And I looked at it and I said, well, what if we forget all the features and we just looked at one feature? Because this seemed particularly interesting to me. Do you personally know someone in your local community who has COVID-like symptoms? So, I thought, well, there is a world beyond machine learning, unlike what many people believe that something can be done without machine learning. What if we just look at that? Look at this question. Do you personally know someone in your local community who has COVID-like symptoms? So turns out this connects to a general area of indirect surveys, where you, instead of asking about you, we ask about people you know. Okay, so you may ask, how many people do you know who are in a hidden population? This hidden population is what we're trying to estimate. And this is particularly useful when getting direct data is challenging, right? So, if, let's say if there's a disaster and you're trying to estimate what is the estimated death, right? So you have to ask how many people do you know who died in that disaster? You can't ask if you died did you die in the disaster? You can't ask that, right? So it has to be indirect. And then there are some other instances where indirect would be more useful. Like if it's better to ask, how many people do you know who are alcoholics, rather than are you an alcoholic? So, but this has been used in questions like this also are out there for COVID-19, as we saw in that survey. And the typical approach to deal with these questions or these responses is what they call network scale-up methods. So you would ask that question, how many people do you know who have this property, who are in this hidden population? And then you'll ask, how many people do you know in general? How many people are you reporting out of? And you get this NI, right? And then you have the XI, which is out of them, how many people tested positive for COVID-19? And you do XI over NI, and this is the estimator. So you just take the average of all these responses, the fractions, and whatever comes up, that's your estimate of the hidden population, the prevalence of the hidden population. By the way, please feel free to stop me anytime you have a question. We don't have to wait until the end. There is going to be a lot of math here, but I believe it's elementary probabilities, and there's nothing that requires any advanced mathematics to understand. So the question I asked is, what if we don't have the reach? Particularly because in our data, we didn't have the reach, right? We didn't have the information of how many people are you reporting out of. But also, getting an accurate measure of reach is difficult. If I were to ask you, how many people do you know? 15, 45? It's a hard number to come up with. But if I ask you, how many people do you know who have taken the influenza vaccine? Oh, there may be 2 or 3, whatever comes up, whoever you know about, you can tell me that number. But how many people you know in general, that's a hard question to answer. And then it also has an inherent assumption, implicit assumption that each individual has equal probability of finding someone in the hidden population. And that's why you can do this division, and mathematically you are okay. So the question is, can we get something useful without asking this question of reach? So what will happen if we just take the average of XI, the responses, rather than XI over Ni. So in this work, what we have shown is indirect, or this average of xi. This is almost always better than the direct question. Right? Direct question meaning like, do you have this property, versus indirect, how many people do you know who have this property? So we show indirect is almost always better. And then we show a little smoothing of responses over time as well. So we have these survey data over time and responses over time. So we're always tempted to smooth whenever we have this any points over time, but a little bit of smoothing is good. That's what we have shown, and we'll see what that means mathematically. And this applies to surveys over time, like infections, vaccine uptake, political opinions that may evolve over time, and so on. Okay, so the key to understanding this is our latent network formulation. So assume we have this set of all individuals, and a subset of it is the hidden population. And we're trying to estimate what fraction is covered by the hidden population over the entire population. So we define a graph, GT, where each edge, ET, exists if at time t, U will count V when thinking about how many they know are in HT. Okay, so at this point in time, whoever you are receiving information from, you are connected to them. That's the idea. You don't have to know exactly, we don't have to know exactly what that graph is, but we are just claiming such a graph exists. And depending on how we reformulate the question, we can restrict edges, right? So suppose if our question was, how many among your household and your immediate neighbors have tested positive for COVID-19? Then we're restricting the possible incoming edges, right? So we can restrict the graph. Okay. And there's a key assumption that we're making, which we believe is very reasonable. So above is the formal statement of the assumption, but what that means is a node's probability of finding an infection around it is independent of its degree, right? So suppose I know you and I'm a popular person and I know many people. Just because I know you doesn't mean you have higher probability of infection or lower probability of infection. Right? This is just a matter of knowledge. Like you could be Twitter followers and have nothing to do with actual interaction, right? So this is the assumption that we're making, and we believe this is very reasonable and also much weaker than the traditional assumption of network scale-up methods, where they assume each node has the same probability of finding an infection around it. Let's say someone lives in an isolated town where the infection never reaches, right? So that assumption will not hold there. But we don't need that assumption. Okay, so the main thing that we'll prove here is, let's say XT is a randomly selected indirect response. And what we prove is the expected value of XT is the average degree of the latent network times the fraction that you're trying to estimate. So just with that assumption, you can prove this. But we have this average degree, right? We don't know what the average degree of the latent network is. The network is latent. But the nice thing is, it's a fair assumption to say mu d, this average degree, is constant over time. Like at any given point in time, there's no reason that on that next week, everyone knows more people than the week after, right? So, and we also see this in data where they were not talking about everyone but they were talking about household size collected over time. And you see that the household size roughly remains constant over time, right? So because mu d is constant over time, our estimate is off by just a constant factor. So we get ft scaled by a constant factor. And if we have any other source of data, we just need one point in time to calibrate and find what this constant factor is. That makes sense, right? So yeah, we are losing something in the sense that we have this mu d constant factor, but we get the trend on expectation, we get the right trend over time. Okay, so then the question comes, well, we have to show that one thing is better than the other. How do you do that? So defining better, how do we show estimator xt is better than something else, which is yt? And yt for us will be asking directly, like, do you have COVID, or did you take the influenza vaccine? Whatever data we're trying to collect. So informally, what we can think about is we can analyze the deviation from the truth. How much deviation will be obtained by xt and how much will be obtained by yt. But more formally, think of, you give me a constant lambda, and then we will show that xt is less likely to deviate from truth by lambda than yt. Right, so mathematically, the deviation from truth that you see here, this is less likely to happen than the deviation from truth by lambda in yt. So if this happens, then we can claim xt is better than yt. Okay, so we have shown the expectation, we have calculated the expectation of xt, but whenever we are trying to do something with these kinds of expression, you need something more so that you can find better bounds. And that's why we would like to analyze what is the variance in xt. And to do that, we have to take care of one extra thing. So for a pair of nodes v1 and v2 with a common neighbor u, the expectation of the state of infection of v1 and v2, again, is independent of the degree of the node that they're connected to. Again, so like if you and you, if I know you both, probability of you both being infected has nothing to do with the fact that I know you both, or nothing to do with how many people I know. That's delta u. Delta u is the in degree of u, right? So just because I'm more popular or less popular shouldn't affect how the two people that I know, whether they are infected or not at the same time, right? That's another assumption. And so that's the first part of the equality. And then we say that this is equal to some number phi t times ft. And this phi t in a way measures independence. So we come up with this measure of independence. And then with that in mind, we can derive what is we can find a bound on the variance of our xt term, which is the bottom equation. So now we are able to bound how much variance we can observe in our indirect response. That's the main thing on this slide. Okay, so now we can compare direct versus indirect, and whenever we have the mean and we have the variance, if you pray really hard to central limit theorem, good things will happen. So we assume that we have enough samples on every day that central limit theorem applies. And with that, we prove what we set out to prove, that for any lambda greater than 0, this scaled estimator xt over mu d minus ft is the truth. So the probability of deviation from the truth by the indirect measure here will be less than the direct measure, as long as the degree distribution follows some bound. So there was this latent network, right? That has some variance. As long as the variance is not very high, this result holds. And then we show that this bound is actually very reasonable. You have to create a very adversarial network with very, very high degree variance for this result to fail. But in realistic situations, this will usually hold. Okay, so far we have just shown that at any given time t, you have direct versus indirect. Indirect is giving you better results. But we have these results over time. So can we leverage the fact that we have these responses over time? So we have indirect responses over time, and we're tempted to smooth. should we smooth and by how much? And we also note that smoothing is actually like aggregating. So, it basically increases the number of samples you have, right? Because you're smoothing, you're adding a bunch of samples near you. So maybe it leads to better estimates. It seems like it would, but smoothing can also deviate our estimate from two numbers. We could over smooth, right? So if you have a signal and you do a lot of smoothing, eventually you get a flat line. So that's not good. So clearly, maybe a little bit of smoothing is good, but too much smoothing is bad. Now, fortunately, we can claim that the underlying process has some level of smoothness. Smoothness by itself doesn't have a formal definition, but we can define it in different ways. So here are some ways to define it. And again, let's not worry about the lemmas, but I'll give you what the summary is. So first lemma is saying that smooth curves do not change rapidly if the first relative difference is small. First relative difference meaning like delta x at any time, or delta g, we're using g here. So delta g at any time divided by the function value itself. So smooth curves do not change rapidly if first relative difference is small. And then the second result we prove is smooth curves do not deviate from much from local averages if the second relative difference is small is missing. Okay, so it's good. If you have a smooth curve and you take averages of a short window at any given point, the value you will get will not be too far from the actual value that was there at the point. If you have highly noisy curve, then you might get more difference. But for already smooth curve, you won't get much difference. And how much difference you'll get, that we have derived here. So then we consider different types of smoothing, and then we'll derive results for each. So consider the weighted smoothing, where nt plus I is, or nt at any point is the number of samples you have. So we're doing a weighted smoothing by number of samples you have. Seems reasonable, right? And then we show that for a given acceptable fractional error, smoothing by W is good if lambda is not too small. Lambda, again, remember, lambda is the acceptable error that you're telling me that I'm willing to accept this much error lambda. In this case, it's fractional error. And then we show that for a range of lambda, again, indirect will be better than direct. Something missing here? No, the smoothing will be better. So smoothing of the indirect response will be better than unsmoothed response if this holds. And looks complicated, but the summary of this is smaller first relative difference allows us to use larger windows. So clearly, if you're already very, very smooth, then you can take larger windows. If you're not too smooth, you should not take larger windows. And with this, you can calculate, you can do sort of a search of what is a large window, what is a small window. And here you can see some of the results. So these gamma sigma square, gamma f, these are the terms that appear in this equation here, right? So you want this gamma f and gamma sigma square, you want both of them to be small. And you'll see as we are increasing W, these gamma values also increase. So gamma equals 1 gives you very small values, but as you increase the window, you get larger. By the way, this is actual case curve from California of COVID-19 cases. And we have removed all the anomalies and all the weekly patterns that emerge in these types of time series. And then you get this smooth time series. And then we're analyzing what is the gamma values here. Okay, so then we do a bunch of synthetic experiments. So we emulate an SIR-like model with changing RT. So if you don't know SIR, it's typical compartmental models, as they say, where everyone is at any given point is either susceptible or infected or has a past infection and has recovered. But with changing RT, what is RT? RT is the average number of infections that that is being created by an infected person. So we have changing RT, and this emulates how in reality, you get multiple waves, and that needs to, for that to happen, you need a varying RT. So at times, people are less infectious. At times, they're more infectious, either because there's more contact or there's a different variant that is inherently more transmissible. And then there are different parts of the simulation parameters that we change. By the way, this is on a power law graph. So we deliberately used a power law graph because these have higher variance, right? And we know that too much of variance is bad for us. So we sort of like set kind of an adversarial setting, but not crazy. This is still realistic network with k to the power -2. So then parameters we vary are you have the approximate average degree. You have the upper limit on number of responses you will get. You have limit of number of nodes that can be collectively covered. What this means is you might have millions of people in the graph, but let's say I have put a limit on number of samples I'm going to collect per day. Let's say only 100. These 100 will only cover certain number of individuals, right? So I don't have to, just to speed up my simulation, I don't have to consider all millions. I only have to consider which are the nodes that are covered by only these 100. So this is more of a simulation trick to accelerate the simulation. Then there's this accumulation, which is number of days over which responses are accumulated. What this means is, suppose you have daily responses. So what if we aggregate this over a week, all responses in that week? So that would be the accumulation. And then there's the period, which is time window within which we count the hidden population. So you don't ask how many people do you know who have taken the vaccine. You ask something more specific. You ask, how many people do you know who have taken the vaccine in the last week? So you get like sort of an incidence data, right? Or let's say in the case of COVID-19 or some other disease, influenza, you would ask, how many people do you know who tested positive in the last 7 days? So you can get the trend rather than just a cumulative value. So we ran multiple simulations over these combinations and generated enough combinations that we have about 84,000 simulations, and we're testing our methods over all these simulations. So the first thing we see is this is just a sample curve with a particular setting of the parameters. And we're trying to compare here two things: direct versus NSUM, which is network scale-up methods, versus indirect. And then we're also trying to compare weighted versus unweighted average. What happens? So the top is indirect estimates. First thing to notice is indirect estimates, they look closer to the underlying true curve, which is the blue line. Then each of these three plots have a yellow line and red line. These are weighted average and unweighted average. And we don't see a clear difference between the two. It's hard to say which one is better. So our theory, all the derivations are for weighted average, weighted by the number of samples. But turns out unweighted average is also not too far. Okay, so there are many results that are discussed in the paper. We'll focus on a few here. And this is what happens if you increase the length of periods. Let's say, yeah, this is the correct. Okay, just making sure I have the right slide. So first thing we note is larger period implies higher number to be estimated, right? So if I were to ask how many people tested positive in the last 3 days, that would be a smaller number than how many people tested positive in the last 7 days, 14 days. That would be a larger number, right? So larger numbers are easier to estimate. If you have a lot of prevalence, then those are easier to estimate. So what we see here is 4 values of period. Within each box plot, you have indirect NOS means no smoothing. So you have three entries for indirect, 3 for unsum, 3 for direct. NOS is no smoothing, then weighted average WA, and unweighted average is UA. Okay. So what can we see here? Weighted versus unweighted average have similar results. That's what we see throughout in all the plots, right? You can see. Then we see smoothing is good. So compare the higher box with the lower box. The no smoothing is high up there. And then indirect is better than unsum, and unsum is better than direct. This is the trend that we see throughout. The differences reduce as we have higher period, but in general, indirect is better than direct. Indirect is better than unsum, and sum is better than direct. Then for smoothing window, smoothing by 1, 2, 4, or 8. Now, this is over multiple accumulations, multiple periods. So that's why you see that variance. But again, what you see is as we are doing more and more smoothing, initially, it seems like errors decrease a little bit, but then they increase again, right? So that shows too much smoothing is actually not good. And again, we see similar trends where indirect is better than unsum and some better than direct. And some smoothing is always better. Then these are the results on actual COVID-19 case data, the officially reported data. And we're checking how different estimation methods, direct and sum, and indirect 1 and indirect 2. So the first column is based on household. So there are 2 indirect questions in this data set. One was, how many people in the household tested positive? And then the second one was, how many people do you know in your community? One is broader than the other. So you could use this both indirect questions to get these 2 estimates. We see that for all cases, the indirect result was better, except for this one case in, I think, Pennsylvania. But again, in general, both indirect questions, indirect responses were better than unsum and direct. So then the question is, well, I ask you how many people you know who are infected, and maybe you have some biases, maybe you always overcount, maybe you always undercount, right? Some people believed it's fake and it's made up thing by the government. They'll just say, oh no, zero. I don't know anyone. You always see this stuff in news, but I don't know anyone. So there might always be this sort of some people are underreporting, some people are overreporting. So what we prove is, suppose there exist these groups with consistent biases, that some people will always underreport by a fraction and some people will always overreport by a fraction. As long as these are consistent biases, what happens is we're just scaled by a different constant. We still get the right trend over time. We're just scaled by a different constant, the B, which is a function of how the biases are in the population. So it is still better than honest direct reporting. So dishonest or biased indirect reporting would still be better than honest direct reporting. So why is that? Why is that? Well, first thing is we have, first, let's agree that indirect is better than direct in case of honest reporting. Okay. And by better, we mean, well, it's not, you don't get the exact numbers, you get the numbers scaled by a constant factor. But if you know that constant, then you have a better estimate. If you don't know the constant, you still have a better estimate of the actual trend, just maybe scaled by some Y value that you don't know. Now, when you have biases, so we're talking about a certain class of biases where there are these groups with consistent biases, meaning like, let's say from group J, if I ask you and the true number was X, you will report alpha J times X. So you're always underreporting or slash overreporting by a constant factor. If this happens, then when we look at the expression of the response that you get, turns out it's just off by, again, a constant factor. So again, if you knew the constant factor, then we're good. If we don't know the constant factor, we're just off by that factor. We still get the trend right. So as far as the trend is concerned, dishonest, biased reporting, indirect reporting is better than honest direct reporting. Yeah.
So does this assume that the size of the dishonest groups are consistent on both sides? So are you assuming basically that the people filling out the survey, there's the same number of dishonest reporters for over-reporting as there are?
No, not same number, but they're consistent over time. So this QJ is the, let's say, fraction of people in the population who whose reports are off by a factor of alpha J.
Okay.
So this could be any number, but they just need to be consistent over time.
Okay.
So it shouldn't be like on Tuesday, everyone is, maybe on Sunday, everyone is more honest than Saturdays and other days. Yeah. We don't assume any seasonality in honesty. And I think this might be, oh, okay, so this might be the last slides, yeah. So the whole theory gives us some idea about survey design as well. So one thing is we noted that the degree variance should not be too high, which in most realistic situations, it seems like, you know, I think we are okay based on some analysis we did. But we can also ensure this by properly formulating the survey question. So let's say, instead of asking how many people you know in general, you could ask among your and your 2 neighboring households. Just make it more specific. How many do you know who have this property? This way, you're restricting the degree of each report. Then we also note that you can construct targeted surveys. So when we're doing direct surveys, right, you have to ask people who you are actually counting. But when you're doing indirect, the population that you're trying to count doesn't have to be involved in the surveys. As in, you can, if you are trying to understand how many people are hospitalized with influenza, you don't have to ask people who are likely to be hospitalized. You can ask healthcare workers, how many people do you know who were hospitalized in the last week? And that way you can get the trend over time. In that case, V would be sort of all hospitalized patients, H is the influenza patients, but the people you're asking is only a subset of V. Well, not even a subset of V, it's some other set, but they have the knowledge of V. And this is my last slide, so I'll stop here and take all your questions.
Thank you, Ajitesh. Questions? Well,
So you know, you run this on COVID. Do you have the results? I mean, weren't you in this? There's like a competition, and it's probably one of the backup slides. I mean,
no, there was this. No.
That was the result.
Yeah, there was this.
But we didn't have like one that was running for the whole country. Like the COVID competition, wasn't it like a more comprehensive competition?
No, this wasn't for the competition. So that was for forecasting. This is basically kind of nowcasting, right? So
okay.
So
confusing the
right.
Because I know other work that you're talking about.
Right. So this has nothing to do with all the forecasting stuff. This is basically, you know, if we didn't have cases, which is the case now, it's not overload the word, but March 2023 is when the emergency ended, and you don't have, you only have hospitalization signal. You don't have any other signal, right? But people still have these home tests, right? So you can still ask people how many people you know who tested positive. There will be some underreporting because people don't talk about it as much, right? But you'll still get the trend. And again, the underreporting, you can think of it as a bias. So you won't be able to recall everyone just because you don't have that information. But whatever information you have will give you the right trend. And that trend itself is a useful signal to, let's say, detect if there's going to be rise in hospitalization. If there's more infections in general, then you'll have more hospitalizations 2-3 weeks from now.
So overall, can you put it in these results in perspective, in practical perspective? Let's say like now with this indirect estimation, you're correcting, you're like more accurate than what
Yeah.
may have done using direct, like.
Yeah.
So what? What are the implications?
So yeah, implications, I would say, I think whenever possible, we should not
I
do
understand
direct
the
at all.
generic implications, like,
Yeah.
but in the context of COVID, like,
Oh,
have you
in
guys
COVID.
actually done some estimates about like, would people have allocated resources differently? What kind of,
So,
like,
yeah,
translates
yeah.
that into human cost or some kind of
yeah.
like,
Yeah, so the main concern today is because a lot of signals have dropped. Doing any hospitalization management is very difficult, especially now that we have COVID is sort of an extra burden with the already existing winter burdens of influenza and seasonal burdens of influenza and RSV. So it's very useful to know if there's going to be an uptick, even that, like not exact numbers, just tell me if it's going to increase in the next few weeks. But even that has been challenging now because we don't have other signals or let's say the leading indicators of increasing hospitalizations. So having anything like that would be useful. Now people are looking at something like wastewater. So that has emerged as a new signal that you can have sort of a leading indicator of increasing hospitalization. But yeah, this gives you an extra signal, which is more reliable than direct.
does this apply to things that are not human-based? Like, for example, wastewater? How does this apply to wastewater tests?
To wastewater tests.
Are similar issues of underreporting essentially applicable to sensors that are not humans?
Yeah. So for example, wastewater has a bunch of issues that we have to understand. So
But there's no degree, right? There's no. What would be the equivalent notion of like how many people you know, like this, the whole like social
that would
network?
be, yeah. So here we have a constant factor, right? The average degree. So the whole trend is off by an average degree.
Mhm.
Right. In wastewater also, the whole trend is off by some constant. And that constant has to do with average shedding, and they do some sort of normalization. So there's a particular virus that humans always shed.
Mhm.
And assumption is we consistently shed the same amount over time. It's in our fecal matter. So then you can use that concentration as the denominator to normalize for the whole trend.
Mhm.
So the people do these tricks to find ways to normalize, but yeah, it's not like there's no network network interpretation there.
But
because you're
would
just like-
would this theorem somehow help for that kind of analysis or not, or they're already doing
I
it
don't-
correctly?
Yeah, I don't think it will help for wastewater in particular, but I think it helps for most of human reported surveys, right? So political opinions. We know that political opinions change, but they change slowly over time, right? There might be individual anomalies on a single day. Someone said something and maybe there's a change on that particular day, but overall it's sort of a slow change. So actually our colleagues, they also tried to do prediction of some election outcomes, and they were successful by using the indirect survey. So they were asking, how many people do you know who's voting for this candidate? Instead of asking, would you vote for this candidate?
So, I have a question. So I think, so the contribution, these indirect surveys have been happening. This is like a known technique that happened for a while, no?
Yeah.
The contribution is like to use as the sum, as a proxy for when you don't know the denominator, no?
Right. So we're saying, forget the denominator. In fact, it's better
it's hard to get and so on. So you
Yeah. And even if you have it, it's actually worse than just using the numerator.
Well, so my question is then similar, maybe related to what Vista was saying. So what other so have people used these specific results for other tasks, finding other things?
So people
politics seems a bit hard, but because
why?
No, because I mean it's more what you think. I mean, there's not like a truth in the sense. Like actually, maybe you can ask something like how many I don't know, how many people you know that their car was burglarized? I mean, their catalytic
right.
converter
Yeah,
was
yeah, yeah.
stolen or something like that.
Yeah.
If you've been next door, you know what
Yeah,
I'm
yeah,
talking
yeah.
about.
Yeah, yeah.
Don't go to next door, by the way, ever. No, don't use it on
No,
networks.
I have
Not
a
evil.
ring. I have ring, and it's every day there's one person.
Yeah, so, but okay, but that's kind of wrong, because that's not the right question. I mean, because you don't know that person, you just read something on social network.
Yeah, yeah.
But I mean, people like social scientists that use this type of methods use this new method, I guess, that you propose, or
No,
they use the classical
it's
one?
new, and I would like everyone to use it, but it's new, and I'm trying to advertise.
So I
it
guess the
too.
question, what would be the cool method, a cool topic, a cool area to use
I
this?
think a lot of anywhere where you're trying to get a public level information, well, so like substance use, how is it changing over time, or mental health?
Yeah, but you have to, I think the question is you have to actually know somebody. So the person
Yeah.
has to tell you about something, not their opinion, but something of truth. Like, I know somebody who died of a fentanyl overdose.
Yeah.
Which I don't, but I
Right.
assume that if you track that question, then
Yeah.
you'll see the trends.
Yeah.
Because
Yeah, and by the way, you don't have to only report other people. You can also ask you or someone you know, right? So
yeah,
you can have
both.
self-loops.
I mean,
You can have self-loops in your network.
yeah.
So it's not like you're missing out on any information.
So can you actually go back to which is the slide that summarizes the algorithm? What would in a sense,
Well,
something implementable, so people maybe they don't want to understand all your theorems, they just want to know,
No,
what do I do
this
with my
is the
data?
algorithm. Like, just
Interesting.
don't. Yeah, algorithm is very simple. Ask people how many people you know who belong to this or hidden population.
And then?
Just take the average. That's it, and that's your point for that day. Okay, so that gives you how many. What is your estimator for that day? Next step is if you want to smooth. Yes, then there's an algorithm. Then there's an algorithm right here. Then there's an algorithm to search for the right double of the smoothing method. But that's already like the next step. First step is just do the estimator without the denominator. Just ask how many people do you know who have this property, take the average. That's it.
So
And that gives you a trend, but that only gives you a trend.
Yeah. So that's why this is useful when you have a trend, rather than just you're trying to estimate just one thing at a given time. That is.
Yeah, so that's why I'm saying that the algorithm is more and then you do something with that average, which is to estimate the trend. And you can then kind of confidently say you're getting the right trend.
Yeah.
The absolute average maybe doesn't mean much.
No, the average is enough for the trend.
Yes,
It's
to get
better
the
than
trend.
Yeah.
To get the trend.
Yeah. But so I can give you another example. So sometimes you have a way to find that constant. So in surveys like this, there were times, so you also have the direct response and indirect response, right? There are times when prevalence is very high. When things are very high, direct and indirect will be similar. The response, your estimates will be similar. So then for that day, you know what the exact value was. If for any point you know the exact value, you know the constant. And then you can rescale your entire trend based on the constant. So you can use these tricks if you're really interested, not just in trend, but exact value over time.
Capturing all of these steps in an actual algorithm that's understandable by somebody who just wants to follow the best practice would be a very useful thing to include.
Well, don't you have a framework to do this, like to do the surveys, or didn't you have like a framework to collect this kind of survey information?
Yeah. So that was what IMDA people were doing. Yeah.
Just happen to know the MDR people. That's
Yeah.
In a sense, is there some exactly like a package or a thing that I can just run? I have this data, I just want to plug it in something and get the numbers. And not worry about how it's done.
No, the question is more like you have to collect that kind of data. I don't know if
I think, as I said, social work people would follow up and let's say create these surveys,
right.
but then after that, they want to be able to plug their data into something that will do this for them easily.
What did they use actually? I don't know what they use. I came to this talk part to understand what they have done. But what they had like I know they asked people who you know, but how did they collect the data? Did they send an email? Did they have an app?
No, they had a website.
Like a website, and then people just capture.
I think they tried to. They also had an app, but it collected in the same database.
Because I mean, that's, I think, maybe what you're asking, is like, you have social workers asking questions, they can go with an app, but people can self-select and go to a website.
No,
to
that's
report.
not the question I was
No,
asking.
the question,
For social science researchers that might, in whichever way, maybe even paper surveys, collect this kind of
Well,
indirect
where
data.
do they put the data?
Yeah, they want to
System?
put the data into something and get the right numbers.
Right. Yeah, so at the highest level, the algorithm is really just ask how many people tested positive for COVID-19 and then take the average of XI. Just the average, that gives you a point. Do it over time, and that is a better estimate of the trend over time than anything else.
You're going to Excel spreadsheet to do this. It's not like you need some complicated computation.
Yeah. No. So I know I agree. You need a little bit of complicated algorithm if you want to find out the optimal window for smoothing the trend. So yeah, then for that we have the algorithm. Yeah. So that's the algorithm for finding the window for smoothing.
So have you looked at what's the sensitivity? I mean, I don't know what the right word is. I mean, there's some events that are so rare that you won't be able to detect anyway. So is there like a threshold on can you compute what the threshold is? Like fentanyl overdoses. I mean, I don't know anybody who has fentanyl, but maybe in a different region of the country, which is more prevalent. I mean, that's only a lot of people.
Yeah.
But is there some kind of minimum number? You need a prevalence of the event of 5% or 1% or something like that, because otherwise it may not be.
Yeah, I guess we do have the.
Is there some theory on that, or?
No, I think that's easy. We just haven't done it, but you have the mean and you have the variance, and with that you can apply Chebyshev to find what's the with how much probability you can detect. But most of the theory here was to just compare rather than find that exact number. Just compare direct versus indirect, smoothing versus no smoothing. But yeah, actually finding that number is relatively easy. Right? Just use Chebyshev.
Any questions from online?
No, I don't see a question. Okay, no question.
I think this was a question
Oh, yes,
before.
Yeah, I had a question around, so it seems like the way, or I guess maybe your future work would be related to how the questions inform. So you give an
Yeah.
example of, if you ask how many people around you within the 3 houses that you live in are infected, right?
Yeah.
And it seems like that type of question can cause somebody to either not provide an answer, or if I don't know, if I really don't have an understanding of the question or the other 3 houses,
Yeah.
I can only tell you about my house. And so it seems like the next work, that affects your smoothing algorithm, if I understand, right? Because if you ask the question a certain way, then that means you're going after a broader audience, but then I can't provide you info.
Yeah. So that doesn't affect the correctness, but yeah, that may affect the coverage, right? Like you're saying that I might not be friendly with my neighbors, but I might be better able to report about my coworkers. So I don't know what the right question is.
Yeah, because it seems like it goes more in the direction of, because I think your argument from the beginning was people are less likely, particularly with this type of stuff, less likely to give you a direct answer. So I'm less likely to tell you more about me. So it seems like there's the way you frame the question is going to get you better to knowing the right answer versus to not getting.
Yeah, and I think that depends a lot on the type of thing that you're trying to collect, right? So COVID-19 might be okay, right? I might be willing to tell you that, my wife was tested positive, but something else as like, substance use.
Yeah, the fentanyl example that was used, or like if you ask the question, like, if you ask me a question like, do I use fentanyl, right? Like, I'm not gonna answer it, right? But if I say how many people I know died, maybe I'm more likely to give you. But it seems like also like, so even when it comes to the framework of going to, say, social workers or how to use these, depending on how close to accurate you want to be, it seems like some understanding of how to frame the question.
Right, yeah. So framing of question, like you pointed out, there are two things. One is who is likely to report stuff, like on, some things you won't report about yourself or your family or your maybe close friends. But there's another thing about just mathematically trying to have the variance of the degree low. Right, so we're trying to avoid situations like, Tom Hanks gets COVID and everyone knows, right? And that doesn't affect us too much because that would be an anomaly in the trend overall, right? But still, we're trying to avoid that kind of situation where there's this huge variance in degree. So somehow when you're thinking of the right question, we have to think about both of these. Who are you likely to report about? And I don't want to have you report about 1 million people, across 1 million people, just like limit that set.
Yeah, and the other thing it made me think about too is I guess comparisons on incentivized surveys. So like, say for instance, even when the COVID surveys came about, there was a random raffle. If you tell us your COVID results over time, you may win money or you may win something, right? And of course, in the field of surveying, they use that method a lot to try to get information. So does that, I would imagine that increases the accurate results more than not incentivizing somebody to ask them directly, but then those compared to say these methods here, like how you gather information. Of course, they're all different ways.
Yeah, so actually, not this data set, but what our colleagues used, they did have incentives. So like you get €1 if you do the survey, and major part of the grant was just incentives, what they were running, right? I don't know if incentives affect correctness. I think incentives do affect participation, but correctness, like, so they will have in the data when someone says, I know 1 million people who have COVID, right? So they saw these things and they would manually remove those that are clearly incorrect.
So this discussion about incentives maybe things like, because they can create bias, but just generally there's bias.
Yeah.
Let's say you have a social network.
Yeah.
And you just oversample one part of the social network. Or you have a spatial network, neighborhoods, and you oversample people from a particular neighborhood and you ask them how many of your neighbors got break-ins.
Yeah.
But you somehow have many people from one neighborhood and very few people from another. Now it's like.
Yeah.
So isn't this whole thing having some assumptions here?
Yeah. So there the assumption is you can only gather information about the part of the population that your respondents can cover. Right. So suppose I'm only asking this to USC students, let's say. Then I cannot gather data from New York, for example, maybe.
Yeah, but even within that, let's say USC students, right? But you take 90% of them that live on this side of the university, only 10% of this side of the university.
Yeah.
Now you're suddenly having much bigger weight on the crime rate on this side of the university. So there is some explicit assumption that you didn't state here.
Yeah, so the assumption will be that the respondents are random.
And that's very important.
Yeah.
I think that's very important to make explicit,
Yes,
right?
but so either that, or you think of you'll only cover the radius of your respondents.
But it's not, again, the radius is USC. I've covered actually all of USC, but I've covered it.
Oh, so you're oversampling one part.
Yeah.
Yeah, okay, right, yeah.
So that then is still biased.
Yeah. I mean, so in this entire thing, we are only trying to estimate, this thing called FT. So if you have biased samples, then FT itself is biased, right? FT itself is different. So the hidden population, you're only focused on the hidden population of where your biases are. But yeah, it's true, it's fair. So the respondents ideally have to be randomly selected.
So can you extend this to then? So you're assuming that's only like one uniform kind of hidden population, but in reality it will be subpopulations that may behave very differently. There will be some group of people in which the virus transmits very quickly, very easily because maybe they're not vaccinated, whatever other groups are.
Yeah,
It's
so,
harder.
so,
So is that part of the framework? Can you kind of?
no, so we don't have to have the prevalence uniform at random. For that, we have this assumption is the key. That it has to be independent of the end degree of who you're asking. Right, so suppose you asked me about, like, the question was asked to me, how many people do you know? Right, and suppose I know you and you are in the hidden population. You being in the hidden population has nothing to do with my degree.
Yeah.
Right, so let's say there's high heterogeneity spatially, but there is someone of degree 5 there and there's someone of degree 5 here as well. Right, so knowing the degree doesn't tell you whether you're likely to be more infected or less infected. That's the assumption.
My question was like, I don't know, let's say it's like probability of getting vaccinated. So maybe for the flu or something. So
Yeah.
let's assume that everybody I know, I mean, let's say I know 10 people, but it doesn't matter how many I know.
Yeah.
But everybody I know is actually vaccinated against the flu.
Yeah.
But I'm part of some subpopulation. Maybe
Yeah,
in
so-
subpopulation, that person, everybody that person knows is not vaccinated at all.
Yeah.
So are you saying that you don't need to differentiate between these two different
Right, because
populations?
let's say you reported out of 10 people, all 10 are vaccinated. Someone else in the world knows 10 people and none of them are vaccinated. So it balances out. Like you are telling me 1 point in the distribution. You are 1 point in the distribution, but the actual probability is independent of whether you know 10 people or 12 people.
Yeah, but you're assuming some kind of average geographical. I mean,
Yeah,
in
that's-
reality there will be
No.
geographical variations.
So this is independent of the geography, right? This is independent of the spatial distribution or any kind of distribution. But yeah, I mean, if in the real world it happens that people who know 10 people, there's something special about knowing 10 people. That if you know 10 people, then all 10 are vaccinated. If you know 5 people, then none are vaccinated. If that happens in the real world, then this analysis doesn't hold. But it seems not reasonable.
Yeah. No, it would depend on the people you know, but it would depend on where you are.
Yeah, exactly. So like there are people of degree 5 in region X and region Y. This could be very different, and that's how they will balance out.
So in the interest of time,
Yeah.
because we already passed 3:30,
Right.
I want to thank you for taking so many questions and
Yeah.
for the nice seminar. Thank you,
Thank you.
Ajitesh.
Thank you.
Yeah,